Hello everyone, this is a quick video to go over the Unit 2 practice exam that I did not discuss in class because I showed up and just automatically jumped into the lecture. But I wanted to make sure that you understood all of the content that's on this exam, and I will begin with just a discussion of the first practice problem. It doesn't have its own solution to it. Okay, this is the practice exam itself. Number 1 involves a free body diagram that gives you some information about the item in question. I ask you for a description that makes sense. So we have an inclined horizontal axis. So this is something that is representative of an object that's on a ramp or an incline. I have a normal force that points up along the positive y-axis, so perpendicular to the surface of the incline, and then I have the gravitational force vector. I have it labeled as a weight vector right here, but this is the product of the mass and free fall acceleration. So there's a kinetic friction force vector that points down the slope. We know that that means that this object is experiencing a velocity that will carry it up the slope, but at this point in time, it is experiencing kinetic friction. So F net is also pointing downhill. A way you could achieve this is to give an object a push, not enough to guide it all the way up the incline, but instead a short push that would allow it to move away from your hand on its own. And while it's in the process of moving uphill, it is slowing down. So an acceleration vector for this item would also point toward the bottom of the incline. Number 2 involves a block that's being suspended by 2 cables. We have the values for theta 1 and theta 2, and we know the mass of the block. We need to determine T1 and T2. So we have a free body diagram that is added to the image itself that shows Fg, the gravitational force pointing toward negative y, then T1 and T2 both have positive vertical components, but T1 has a negative horizontal component, T2 has a positive horizontal component. So the block being at rest and not accelerating means that it's experiencing static equilibrium. So I know that the forces in each direction will sum to 0. With the x direction, I've chosen a coordinate system that shows negative signs going toward the left. So T1 cosine theta, the cosine component of T1, is going to point toward the left. That's a negative. And I need to be specific because these thetas are not the same. So this is T1 cosine theta 1. Pointing toward the left. T2 cosine theta 2 points toward the right. Those have to add to 0. In the vertical direction, we have 3 forces. T1 sine theta 1, which points up. T2 sine theta 2, which also points up. And the gravitational force mg. So I'm subtracting that because it points down. That's equal to 0. And at this point, we just need to solve this system for T1 and T2. I chose to write an expression for T1 just out of F net x, so I can plug in the ratio T2 cosine theta 2 over cosine theta 1 when I go back to the net force expression for the y direction. So here's T1 sine theta 1 plus T2 sine theta 2 minus mg. Now T2 is my only unknown. I can just isolate T2 algebraically, and what we end up with is something that will round to 151 newtons when you apply the correct number of sig figs. By the time you have T2, you have a few different options as to how you can determine what T1's value is. I just went back to T1, the expression that we derived from the net force expression in the x direction. And when I plug that in, I get 129 newtons. Number 3 is an interacting object problem. So this is what we spent a bunch of time on in Chapter 7. We have 3 identical blocks. They're all 0.250 kilograms. They're connected by strings that are massless. They're on a surface that's frictionless. And we know that the acceleration is 1.50 meters per second squared. And one of the hallmarks of an interacting problem or interacting object problem is that the accelerations for these interacting objects have to be the same. So the acceleration for A is going to be the same as B, which will be the same for C, even though block C is the only one that's being directly acted on by this force vector. So we need the values of the tensions in the strings that separate blocks A and B and C. This is what the free body diagrams would look like for all three of these items. Block A is at the end of the chain, so discounting the vertical forces that are acting on block A, the only unbalanced force is TB on A, so the force from block B on block A. That exists as 1/2 of a third law pair or an action-reaction pair. That just involves the tension of block A on B. I have another third law pair here involving blocks B and C. So the tension of block C on B is equal and opposite to the tension from block B on C. And then F, this is the external force that is ultimately causing the acceleration that is indicated in the description. Start by writing net force expressions for each of these blocks, and the simplest block to start with is going to be the one that's latest in the chain. It just has this one horizontal force, TB on A. So the entirety of the net force on block A is TB on A. That has to be equal to mass times acceleration, where there's no subscript here because the acceleration is the same for all three blocks. Solve for TB on A. We get 0.375 newtons. The question is asking us for TA on B, so I know that that particular force is going to be the same magnitude, but just in the negative direction. For block B, we have two forces that act on block B. Block B accelerates toward the right, just like all the others, so MB times the acceleration is a positive, but I know that there are now two horizontal forces to worry about with block B. So I can isolate TC on B, because I already know how large TA on B is, and I can calculate F net. That's how you get TB on C. TC on B is 0.75 newtons, therefore TB on C is going to be negative 0.750 newtons. And finally, just do the same thing to block C, where we don't know anything about F, but we know that block C is subject to a tension force that originates from block B and F. The net force is going to be the mass of block C times the acceleration. So when you isolate F, you end up with a force that's larger than any of the other two that we calculated, which makes sense because the force on block F has to be more than what's required in order to get block C to move at a constant speed. So in other words, if the acceleration is positive, then the force acting on block C has to be larger than what would be required to cancel it out. This page is scanned out of order. I apologize, but I'll go to number 4. We have a modified Atwood machine, so different than the two examples that we saw in our lecture notes. Block A is sitting on a surface. That surface has friction. Block B is sitting on an incline that also has friction. The blocks have the same mass, and we know that the coefficient of kinetic friction between each block and the apparatus is 0.15. If we assume that the string is massless, then we can determine the tension in that string and the acceleration. I would suggest that you start with block A because that one is simpler. There are two vertical forces that we know cancel out, the normal force on block A and the gravitational force on block A. And because the kinetic friction force vector acting on block A is oriented toward the left, we know that the velocity vector for A is oriented toward the right. So we know that the system is accelerating toward the right. So the tension in the string acting on A has to be larger in magnitude than Fk for block A. For block B, now I have a gravitational force Fg on, or Fgb, whose value we can calculate. The normal force now is not going to be the entirety of FGB, but instead just the cosine component. The FG sine theta component is going to be directed downhill, and both tension and FK for block B are going to be oriented uphill. So our net force expressions are right here. For block A, I basically need to know what the normal force on block A is, only so I can use that to figure out what the kinetic friction on block A is. But I start off knowing that that normal force and the gravitational force cancel. For block B, I have cancellation in the y direction as well. So I don't have an equal to 0 on this F net y term, but we know that those two force vectors cancel out. And along the surface of the incline, I have the sine component of the gravitational force minus kinetic friction acting on B minus tension. All of that's going to be equal to MB on B times A. So I've decided that down the slope is going to be the positive acceleration direction, or the positive x-axis. I have two starred equations, F net x for block A and then F net x for block B. I can solve each one of those so that I can eliminate the acceleration. That would get me to the tension first. And at this point, I don't need to distinguish between the two masses because they are equal in this case. The kinetic friction acting on block B is going to be slightly smaller than block A because of the fact that block B is on an incline and A is not. But at this point, I can just solve for T. And what we find is that the tension, which is on the previous page accidentally, is 102 newtons. And just like the static equilibrium example, I can go back to either one of the expressions that we have that relate the tension to the acceleration. This is the one for block A that's just a little bit simpler than the one for block B. We can plug in our calculated tension, plug in the kinetic friction acting on block A, and we end up with 1.08 meters per second squared. This is the magnitude of the acceleration of each one of these blocks. Now on to number 5. A highway is designed such that a 1,500 kilogram SUV can move around a curve of radius 210 meters at 25 meters per second without having to depend on static friction. What banking angle can achieve this? So a banking angle or a banked road problem can sometimes involve static friction being present. There are two different free body diagrams that show up in our notes for Chapter 8, Part 1 that show those two scenarios, but this is the case where static friction is not present. That means that the radial force can only come from the radial component of the normal. The normal force in this case is bigger in magnitude than Fg is, but it splits into a sine and a cosine component. So writing a net force expression for the z direction gives me n cosine theta minus the gravitational force. That's equal to 0 because the car doesn't accelerate into the surface of the road. It also doesn't accelerate above the surface of the road. So the normal force is going to be m times g divided by cosine theta. Theta is ultimately what we're looking for. So we can go to our radial net force expression for the next equation in our system. And there's only one force vector that points along the radial axis. It's pointing toward the center, so I can treat that as a positive. So F net radial is n sine theta, but that also has to be equal to m times the radial acceleration. I have it written out as mv squared over r. The normal force shows up in each of these expressions, so if you solve both of them for the normal and set them equal to one another, then we can determine what the angle theta is that allows this particular banked surface to support a car that's traveling at 25 meters per second without relying on static friction. A note about the tangential force, I have it written out here in the F net section, but the direction of the tangential axis would be oriented right into the plane of the screen. So the car moving at 25 meters per second doesn't have an acceleration along that axis, so the net force along that axis is also equal to 0. Number 6, you're asked to coordinate the launch of a satellite that will orbit Earth once every 18 hours. What should the altitude of this satellite be? Earth's mass is given, Earth's radius is also given. So we need to create a scenario where the period of this satellite's orbit is 64,800 seconds. So we know how to relate that period to the position separating the center of the planet and the satellite and free fall acceleration at that location. So you can start by solving this expression for the period for free fall. You can't just plug in a 9.80 meters per second squared and get a period that is appropriate for the position that we're shooting for. So free fall acceleration is going to be 4 pi squared over r divided by t squared. We also know from chapter 6 that we can predict what free fall acceleration should be measured relative to some planet that has mass capital M and some distance lowercase r, where lowercase r encompasses the altitude of the satellite measured with respect to the surface and also the radius of the planet. If we put those together, we have an expression that now just has lowercase r as an unknown. I can plug in capital RE, so the radius of Earth, plus h, which is the altitude, in both of the locations where you see a lowercase r. Now I'm solving for the quantity RE plus h. That'll take a cube root of everything that's on the right-hand side. And then finally, I can just subtract out the radius of the planet in order to figure out h. So for an 18-hour period instead of a 24-hour period, the appropriate height would be something that I could express as 29,000 kilometers. 7 is a vertical loop problem. We have a bucket of water and assume the complete mass is 2 kilograms. It's connected to a string that has a known length and it's spun in a vertical loop. First, we want the minimum speed that would allow the bucket to make it around the loop and most importantly, the water to stay in the bucket. And we want the tension at both the top and the bottom if we know exactly what V is. So starting with that critical speed, let's look at the free body diagram for the top of the loop. There's a tension force that's acting on the bucket. There's a gravitational force acting on the bucket, but that is all. So the net force is going to point toward the center of this loop, and I'm going to treat both Fg and the tension as positives. So that critical speed occurs when this tension shrinks down to 0. If we set the radial force equal to the gravitational force, the meaning of this V tangential changes because we're looking for this critical speed, not just any V, but the one that matches up with a tension of 0. We can plug in the radius of the circle and free fall acceleration. So it takes at least 2.9 meters per second for the bucket of water to complete the loop and for the water not to fall out of the bucket. Now, if we know that the tangential speed is instead 5 meters per second, so safely above that minimum value, at the top, our net force expression is almost exactly the same, only this time we have a non-zero tension. So both of these force vectors point toward the center of the circle, so tension plus Fg is equal to the radial force. And I'm not changing Vt to V critical because this is not the case where tension is equal to 0. Solve for T, and we find that you get 39 newtons when you apply sig figs. For the bottom of the loop, the free body diagram is a bit different. Tension is going to pull toward the center of the loop, but now Fg, the gravitational force, is directed away from the center. So I treat that as a negative. Net force is always going to be oriented toward the middle of the circle. So I have T minus Fg for the tension at the bottom. And all I need to do is isolate T and I end up with 78 newtons. For exam 1, I gave you some pointers on what you could definitely expect to see on the exam. I wanted to do the same thing here. So I'm going to ask you a question about Atwood machines, but it will not be as complicated as the one that was on the practice exam, where you had a little bit of everything. You had slopes, you had friction. It will either be the traditional Atwood machine, where both blocks can only move vertically, or it will be the modified Atwood machine, where one block is on a frictionless surface. Interacting objects is kind of tied to Chapter 7. So think about the homework problems that we had concerning blocks in an elevator, I believe. Also, the problem on the practice exam that had blocks that were connected by strings is one that you should definitely review. You will have a question about free body diagrams that doesn't require that you actually make a calculation, but just you interpret a free body diagram or interpret a situation and draw a free body diagram. I'm going to ask you about a vertical loop, so study the coaster problems from the end of Chapter 8 and also the water and bucket scenario from the practice test. And I'll ask you about an orbit, similar to the one that was on the practice test, or possibly the one that was in the notes. So remember that make sure that you remember how to compute free fall acceleration for locations other than Earth's surface. Once again, I apologize for completely overlooking the review we were supposed to have in this Thursday's lecture. Let me know if you have questions about anything between now and Monday. I will have office hours from 10:30 to 1 p.m. tomorrow on campus, so that's Friday the 20th. This afternoon, I'm going to have to cut one of my office hours short, so I will only be available between about 2:15 and 2:45.